Hello, class. We've been working with weak acid and weak base equilibria for some times now, and we have looked already at creating buffers by adding some soluble salt of the conjugate base of the acid that we're using. Today, we're going to expand that a little bit further and look at what happens to uh, equilibria when you add a common ion. This is something that is common to the acid-base dissociation reaction. So whenever you add something involved in an equilibrium from another soluble source, the equilibrium is going to shift in a direction that reduces the concentration of what you've added. This is Le Chatelier's principle. Let's look at an example. Here's a hypochlorous acid equilibrium. I've included the water to create the H3O plus. That is the most dominant species that's present. But you recall water concentration doesn't change, so it's not involved in the equilibrium constant. So this is the equilibrium between hydronium ion and hypochlorite ion and hypochlorous acid. Now let's look at what happens. Say we're looking at the concentration versus time, and once this equilibrium is established, those concentrations all remain constant. Now it is a dynamic equilibrium, so you do get reaction in both directions, and it can be quite rapid, but the same speed of reaction is occurring in both directions, so the net concentrations don't change. Suppose at some time um, uh, we add a little bit of sodium hypochlorite, which is a soluble salt. Now, you would recall that this would create a buffer from the previous lesson that we had. Now, at some moment, we add that substance into the equilibrium. So hypochlorite ion concentration momentarily goes up. Now what's going to happen? The equilibrium is going to shift to the left, which means this concentration and this one are both going to go down, and the hypochlorous acid concentration is going to go up. Now, a point to note is that the final new equilibrium concentration of hypochlorous acid is going to be higher than we started out with, but certainly not as high as what we put in. And the new equilibrium will be established, and the equilibrium concentrations in this new equilibrium would still equal um, the Ka for the acid that we started out with. And so the old concentrations put together this way with hydronium and hypochlorite over hypochlorous acid would be a constant. Similarly, the new concentration will do the same thing. It'll be equal to the same constant. Again, remember always that only the temperature and the presence of a catalyst are able to affect the numerical value of the equilibrium constant. Adding things to an equilibrium doesn't change the concentration as long as the temperature or the substance you add isn't the catalyst for the reaction, say in the forward direction, or what we might call an inhibitor if it's catalyzing a reverse reaction. Okay. Yeah, this adding that common ion to the solution is called the common ion effect, and we saw its effect on that example equilibrium. Now let's look in general terms about adding acids, sources of hydrogen ion, to a weak acid-base equilibrium. The equilibrium is going to shift in the direction that uses some of the added acid. Now remember, the acid in water is H3O plus. And whatever acid you put into water, no matter what it is, that's acidic, that's going to cause this concentration to go up in the equilibrium that you have established. the pH will decrease. Hey, should. You added an acid. Adding a base. A base is something that reacts with the hydronium ion that's present in the solution. So the base is going to lower the concentration of the hydronium ion in the solution, and that's going to cause the pH to increase. Okay, what do we think it would do? We added a base, so that's exactly what should happen. Now here's a table that we're going to add several different things to illustrate both the common ion effect and the adding of acids and bases. I'm going to see what is the effect when you, on the pH, the pK, the Ka, the hydronium ion, hypochlorous acid, and hypochlorite ion in this equilibrium if I add water to it. Okay, the pH is going to go up. Well, we'll look at that in a minute. The Ka is not going to change because we didn't change the temperature or add a catalyst. The H3O plus concentration is going down. The HClO concentration is going down. And the ClO minus concentration is going down. Now, that's easy to understand. We added water. All we did is dilute everything. If we dilute this, we decrease the concentration of the hydronium ion, but decreasing its concentration increases the pH. Ka certainly doesn't change. So the effect of adding water is just to dilute everything. We'll come back to another point about that in just a moment. Okay, if we add HCl, well, we added a strong mineral acid. So what do you think is going to happen? pH is going to decrease. The Ka is not going to change. We added an acid, so the hydronium ion concentration is going to increase. And now if that concentration increases, what will happen to the equilibrium by Le Chatelier's principle? It would shift left. So this concentration would go down and this one would go up. So this is the effect of adding a strong acid. I used HCl as an example, wouldn't matter. Any acid would do exactly what this line says. Sodium hypochlorite. Now this is a common ion effect. We have added this concentration. This hypochlorite ion concentration has gone up. And we just saw a while ago what that did to everything. The pH is going to increase. Well, why will that happen? Well, if I increase the hypochlorite ion concentration, the Chatelier says it will shift left. That'll cause the hydronium ion concentration to go down and the pH to go up. We shifted to the left. If we shift to the left, this concentration will go down. And this concentration now, remember, we added this, it's going to go up. The Chatelier say does shift to the left, but remember, we added that spike and then it slowly came back down. Now, if I add sodium chloride, well, what's sodium chloride? It's a soluble salt. Neither the cation nor the anion will hydrolyze because it's a salt of a strong acid and a strong base. So we don't expect anything to happen because neither sodium ion nor chloride ion is involved in the equilibrium at all. So this would be the effect of adding any neutral substance other than water. We saw what happens with water, but any neutral salt would do exactly the same thing as this line. No change at all. If we add sodium hydroxide is a strong base. If I add a strong base, it's going to react with the strongest acid up here, which is hydronium ion. It's going to use that up. When it uses that up, it decreases the hydronium concentration. So what do you think that would do to the pH? It would increase. Ka certainly isn't going to change. This concentration, we already said, would decrease. Now, and decreasing this one shifts the equilibrium to the right. So that would cause this one to decrease and the hypochlorite ion concentration to increase. What about if sodium nitrite or potassium nitrite I used here? Well, potassium nitrite is the salt of a weak acid. Sodium potassium hydroxide would react with strong base, would react with nitrous acid to produce this salt. So the salt is going to be basic. We'll discuss that some more. So the pH is going to go up. Now, Ka won't change. So now, if I put nitrite into that solution, it's going to react with this acid, and it's going to decrease its concentration. Decreasing its concentration shifts the equilibrium to the left, would reduce the concentration of the hypochlorous acid, and increase the concentration of hypochlorite ion. So this sort of illustrates, I think, all the types of things that you could add. Let's look at the pH part again. Now, we made a wrong jump. It should not have gone there. It should have gone here. Okay. If we add an acidic substance, the pH is going to go down. In this list, the strong acid we added was HCl, and that causes the pH to go down. If you add a basic substance, the pH is going to go up. Now, water is a base in this because this is an acidic equilibrium. Water acts as a base compared to the acid that it's in. And so we have effectively added a base. Sodium hypochlorite, even though it's a common ion, and we got the correct answer looking just at the common ion effect, it also is the salt of a strong base, sodium hydroxide, and hypochlorous acid is a weak acid. So the salt is going to be basic because it's made from the strong base. NaOH, of course, is a strong base. It's going to make the pH go up. Sodium nitrite, as we said a moment ago, it's the salt of a strong base, sodium hydroxide, and a weak acid, HNO2. So the strong base dominates, so this salt is going to hydrolyze to be basic, and bases always make the pH go up. If you add a neutral substance, the pH doesn't change. And sodium chloride is neutral because it's the salt of a strong base, NaOH, and a strong acid, HCl. So that's not going to have any effect at all. Now, let's look at the last part of this equilibrium is your checkpoint. It might not be exactly the same one that's on D2L, but that's the one that you should use, the one that's on D2L. And it'll be maybe a different example. It could be the same example. And so what I want you to do is just to mark increase, decrease, or no change in each of the columns here. You should work this out individually and then go to the discussion page on D2L to pick up the discussion with each other. I'll monitor that frequently, and if I see any problems, I will jump in and help you. Now, the rest of the lecture deals with solubility equilibria of things that we have normally talked about as being, quote, insoluble compounds, but they are not. Let's take an example. If I take something like Hg2Cl2, that's a solid, and according to the solubility rules, all chlorides are soluble except this one, mercury 1 chloride. silver chloride and mercury and lead 2 chloride. Those 3 chlorides are insoluble. Now, if we put this into aqueous solution, there certainly is going to be an equilibrium established. We will get a little bit of Hg2 plus 2 ion, and we'll get 2 chloride ions. And of course, these are all aqueous. So we've set up an aqueous equilibrium with this. So we can define an equilibrium constant. In this case, it's called the KSP, the constant for solubility product constant. Now, I think you'll see why that is called solubility product, because this constant is just going to be the Hg2 aqueous concentration plus 2, that concentration times the Cl minus concentration. Of course, that's aqueous as well. And there's 2, so the equilibrium constant causes us to put a superscript 2 up there. I'm going to switch pens so it'll be easier for you to read. Now, let's take this same example, and let's suppose that S moles per liter dissolve. So I'm going to have S moles per liter of that will dissolve. And since my KSP, so if S moles of this dissolve, I'll make S moles of that. So the Hg2 concentration is just going to be S, and it was to the first power, so that's to the first power. But when I dissolve S moles of mercury 1 chloride, I'm going to get 2 S moles of chloride ion. So this is going to be a 2S, and that's going to be squared. So the KSP is going to be S times 2S squared, and so the KSP is going to be 4S cubed. So you see, if I can get the molar solubility of this compound, how many moles per liter will dissolve of the compound, then to get the KSP, I would have 4S cubed. Let's take the case of the silver chloride one, just to show you the example. If I have AgCl, silver is always plus 1, so it's silver chloride. If I put that into solution, then I'm going to get the Ag plus concentration aqueous plus the Cl minus aqueous. And the KSP for this salt is, again, if I put S moles of this, I'll get S moles of this and S moles of that. So it's just going to be S times S. So the KSP is going to be S squared for this salt. So you see the expression for KSP and molar solubility depends on the stoichiometry of the salt and the number of ions it creates. So, and this is the pattern that we would see for other things. And likewise, we can now, if we knew the KSP, we could calculate the solubility in either case, but we'd have to be sure to use the correct expression. So the KSP can be determined from a measurement of molar solubility, and the molar solubility can be determined from the value of the from the value of the KSP if we have that available. Now, suppose I start mixing some ions together. For example, if I took silver nitrate and let's just add hydrochloric acid to it. Okay, what's going to happen is the ions do separate. I would get Ag plus and NO3 minus, and the strong acid does separate to H plus and Cl minus. Now, HNO3 is a strong acid, so these ions are going to remain separate. But when there will be a reaction, because when the silver ion bumps into the chloride ion, we're going to get AgCl precipitated, that's a solid, and we would get H plus and Cl minus would still be there as spectator ions, and of course these would cancel out in the net ionic equation. I'm sorry, NO, this should be NO3 minus. So the NO3 minus would cancel here, the hydrogen ion would cancel here. The net ionic equation we would have is Ag plus Cl minus goes to AgCl solid. Now, as we mix these things together, the concentration of silver ion, if I just take pure water and put some silver nitrate in it, the concentration of the silver ion goes up as I add the silver nitrate. And the concentration of chloride ion would go up as I add the hydrochloric acid. And eventually you would reach a point where you would start to see this precipitate. Remember, that's an equilibrium. So we need to be able to determine, will we get a precipitate or not? So you can define a QSP, and the QSP is just like KSP. It's going to be the Ag plus concentration that you have now, not at equilibrium, times the Cl minus concentration that you have now. So if you continue to increase the concentrations, you will reach a point where QSP becomes the same value as KSP. From then on, if QSP then is greater than KSP, you get a precipitate. And you can have silver ion and chloride ion both in the solution at the same time. You will not get a precipitate until the concentrations of product of these two concentrations is equal to KSP, and then it would have to go just a little above that to actually see a precipitate form in the solution. Now, if you have a mixture of ions that could all precipitate, like the first example we did two of them. We had mercury 1 and silver, say if they were both in solution, and I started adding chloride ion to it to get the precipitate to occur. One of these KSPs is bigger than the other one. I don't remember offhand which is which, but as I add add chloride ion to either mercury 1 or silver 1, or silver plus 1, whenever you reach the KSP value, you will get the precipitate to occur. So whichever one has the smallest value of the KSP will precipitate first. So, and it actually does happen sequentially. Uh, 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 Essentially, if the KSPs are different from each other, then, and they usually are, the one that's most least soluble is going to precipitate out first before you even start precipitating the other one. So if you carefully added chloride to these, you could probably precipitate them out one at a time. Now, solubility of some salts is going to be pH dependent, and I think you could certainly imagine, for example, it's not one of the ones that but all hydroxides are insoluble. So suppose I took silver hydroxide. Well, silver hydroxide is insoluble, so it would dissociate into Ag plus OH minus. Now it's pretty obvious that this salt is basic, but a while ago we saw several, if you have the salt also of some weak base, then it would have an anion that hydrolyzes, and it would also be a basic salt. And as you add hydrogen ion or hydroxide ion, you're going to shift that equilibrium. If I added hydrogen ion to it, then of course it's going to shift to the left because the hydrogen ion is going to react with, I'm sorry, got too carried away here. If you add hydrogen ion, it reacts with this to make water, and the water would not redissociate. It's a weak electrolyte. So you decrease this concentration, it shifts to the right, and the solubility will go up. And conversely, if you add a base to it, this concentration would go up, and it would cause the equilibrium shift to the left and become less soluble. Okay, so I need to move my fresh paper so it doesn't get dots all over it. Okay, so some salts are affected by pH. In fact, if the salt is not a neutral salt, its solubility is going to be affected by pH. That is, the salt that is insoluble but made from a strong acid and a strong base, those would be pH independent, but everything else would be pH dependent on their solubility. Now, the discussion here has complex ions and things like that in it. I'm going to go through that very rapidly, but we're not going to have anything deeper than what I'm going to show you here, and I'll point out the things that you might need to know. If you had a complex ion, if you had, for example, silver ion, what can happen to silver ion is if you add, for example, ammonia to it, now we've talked about all the concepts of acids and bases, so this can react together. So if I react these together, it's going to take two of these, but you're going to make Ag plus NH3 H3N on this side, and the pair of electrons is going to be shared by that. I'll pull it back down here. This is one ammonia molecule turned in this direction with its lone pair toward the silver plus ion. And this is the other ammonia molecule. And the whole thing then is actually where the positive charge is. It's a +1 charge. So this is a diamine silver complex ion. And anything with a pair of electrons with any metal ion can do these kinds of things. You did copper sulfate pentahydrate. You've used that in the lab in the hydrate experiment from Gen Chem 1. These 5 water molecules are attached to the copper in a complex ion. I won't bother with drawing out the structure for you now, but the idea of forming complex ions, anything with a pair of electrons is a Lewis base. And when we put those together with a Lewis acid, in this case, you will make a complex ion. So when you get a complex ion, it is an equilibrium as well. The Lewis base is covalently bound. That's what we mean by that pair of electrons. It's a covalent bond, and that pair of electrons is a covalent bond. And it's bonded to the metal atom. And most of the time, those electron pairs go into the d orbitals of the metal and one of the empty d orbitals. Now, if you can form a complex ion, in fact, when we did this with silver, if you took Ag and you had AgCl solid, what can happen, and what we did in the experiment, to confirm that you had silver, you added ammonia. And what it does to the silver ion is it causes this diamine silver complex ion to form. And it's, I'll draw it again down here for you. H, N, H, H, pair of electrons, Ag, pair of electrons, N, H, H, H for the ammonia. Plus, of course, you're going to now have the chloride ion, minus. And this thing is plus. Now, this is soluble. So the point we're making on the PowerPoint is that formation of a complex ion will increase the solubility because it's reducing the concentration of the free silver ion. So this thing would have dissociated to some silver ion out here as a product and a chloride ion in the solubility equilibrium. AgCl would be in equilibrium with Ag plus and Cl minus. So if I add ammonia to this precipitate, I'm going to remove some of that, which means Le Chatelet says it'll shift to the right and become more soluble. So it increases the solubility of slightly soluble salts. And this is one of the ways we actually separate them. Now, the complex ion equilibrium has a formation constant, just like the KSP constant, just like the weak acid, weak base constants that we've seen before. And we can use the formation constant if we wanted to calculate the concentration of the free ion still in solution. For example, we could calculate how much silver ion was still present after we added ammonia to create that complex ion. Now, we're not going to do this in this class. But here's some problems now that we'll go through to look at the effect on solubility of some chromate compounds. Here's silver chromate. Its KSP is 1.2 times 10 negative 12. Here's barium chromate. Its constant is 2.1 times 10 negative 10. Calcium chromate is 7.1 times 10 negative 4. And here is the Ka constant for hydrochromous acid, HCrO4 minus, 1.5 times 10 negative 6. We're going to use these data in some problems. Let's write the solubility expression for silver chromate. So we're going to dissociate to 2 silver ions and 1 chromate ion. KSP is going to be Ag squared times CrO4 2 minus to the first power. So that product, Ag squared times this, is going to always be equal to 1.2 times 10 to the negative 12, unless we change temperature, of course. The KSP for silver chromate, if the what is the KSP of silver chromate? If the solubility of silver chromate is 7.52 times 10 negative 4th grams in 100 milliliters. Now, the reason why I chose this is exactly how I got this number up here. I went to the CRC handbook. It's a great big thick book, maybe 3 inches thick by 12 by about 14, I think. It's a big book. And it contains a myriad of constants and things that are useful to chemistry. It's a very, very good reference book. But it gives solubility of a whole host of compounds, but it gives it in the number of grams that dissolves in 100 milliliters. The solubility of it has to be calculated. So if I took 7.52 times 10 to the negative 4th grams and divided it by 275.75, that is the molecular weight of silver chromate, then that's the number of moles I would have. And the concentration of silver ion then would be twice that many moles, because for every 1 mole of this, 2 of these form, and then divided by the volume at its end is 100 milliliters. So the silver ion concentration in this solution is 5.454 times 10 to the negative 5th. The chromate ion concentration is just going to be half that, because I don't have that number 2 in there. And it's going to be 2.727 times 10 negative 5th. Now, if I square this and multiply it by this, as we have here, square the silver ion concentration, multiply it by chromate, then I get 8.1 times 10 negative 14. This is a typical region. Remember, these are compounds that are, quote, insoluble. You can see they're not very soluble. Okay, now let's look at another problem. Rank the silver, barium, and calcium chromates in order of increasing solubility. Now, the silver ion concentration, KSP value, is Ag2CrO4 is 1.2 times 10 to the negative 12th. The barium is 2.1 times 10 negative 10, and the KSP for chromate is 7.1 times 10 negative 4. Now, you cannot compare the KSPs and say, well, the one with the smallest value is the least soluble, and the one with the largest value is the most soluble, unless they both have the same stoichiometry. For example, barium chromate has 1 cation and 1 anion. Calcium chromate has 1 cation and 1 anion. Now, it is going to be true that this one is less soluble. Barium chromate is less soluble than calcium chromate. I can compare those, but I can't compare these two with this one. So we have to compare the solubilities, molar solubilities instead. So now, if I'm looking at the silver solubility, molar solubility, silver chromate is this, the barium chromate is this, and the calcium chromate is this. Now I can compare them. This one is the least soluble. Then, so barium chromate would precipitate first. It's the least soluble. Silver chromate would be second, and calcium chromate would be the last one to precipitate if I had all of the ions present and added chromate to them. So there is the solubility. Now let's look to see what happens to these if we mix these solutions together. One of them is going to contain 250 milliliters of 5 times 10 negative fifth molar sodium chromate, and we're going to add chromate from this source to 250 milliliter solution that the silver ion, barium ion, and calcium ion are all three the same, 5 times 10 negative 3. And we're going to see, do we get a precipitate? And if we do, what is it? The initial concentration, then after mixing, we're going to dilute by a factor of 2. Each solution is going to go from 250 to 500 milliliters in this test tube. So the chromate ion concentration, we had 250 milliliters. It's going to be diluted to 500 milliliters. Its initial concentration, there's one of these for 1 mole of that. So I'm going to get 1 mole. The molar concentration for the chromate ion originally was also 5 times 10 negative fifth. So the chromate ion concentration now in this test tube with all of these is going to be 2.5 times 10 negative fifth. Now, the barium and silver and calcium concentrations were all, again, diluted by 250 to 500 milliliters, this much. So the concentration is going to be 2.5 times 10 negative 3 in each one of these ions. So let's calculate QSP for each one of them. The QSP for the silver chromate, I'm going to take the silver ion concentration and square it. Remember, it's got 2 silver ions, so I'm going to square its solubility, the silver ion concentration. And the chromate ion concentration is 2.5 times 10 negative 3. If I do the math, I get 1.56 times 10 negative 12 is the QSP. So QSP is greater than the KSP that we had for silver chromate. So yes, we will get silver chromate precipitating. Let's look at the others. The QSP for barium. Barium chromate would have 1 barium and 1 barium and 1 chromate ion. So it's the solubility, the QSP is the barium ion concentration, which is 2.5 times 10 negative 3, times the chromate ion concentration, which was 2.5 times 10 negative 5. Do the math, we get 6.25 times 10 negative 8. QSP is also greater than KSP for barium chromate. Let's look at the other one. We do get a precipitate. For calcium chromate, it's still 1-to-1, so we're going to get the same value for the QSP. But in this case, the QSP is less than the KSP for calcium chromate. So when I mix these 2 solutions together, we will get a precipitate. It'll be mixed with silver chromate and barium chromate, but the calcium chromate would remain in solution. So if I centrifuge this down and took off the liquid and evaporated the liquid, I'd get the calcium chromate that was in the solution. What's the molar solubility of silver nitrate in a solution that is 5 times 10 negative 6 molar sodium chromate? So we've got our KSP is this value. Now, but I'm going to add sodium chromate from outside. So what's going to happen is I'm going to increase the concentration of chromate ion up to this value. And I want to know then that there is and I need to take the square root of that because silver ion was squared. So if I take the square root, I would get the concentration is 4.9 times 10 negative 4th molar in silver ion if I've adjusted the chromate ion concentration to a higher value. So it's still going to be 4.9 times 10 to the negative 4th, for the solubility of silver nitrate in that solution, because the silver ion concentration and the HNO3 has one ion each. The pH is what pH is required to prevent barium chromate from precipitating if the concentration of each ion is this much. Okay, so if this is my KSP value, and if the barium ion concentration is 7 times 10 negative 4, the chromate, highest chromate concentration that you can be present without precipitating is going to be this value. We can solve for it. It's going to be that much, 3 times 10 negative 7. And now we're going to look at pH, and that's going to be affected by the chromic acid concentration, or hydrochromic acid is the second acid for second hydrogen for chromic acid that's going to release the chromate ion that's present. And now this is the KSP for the chromate ion. This acid is going to form in this solution whenever you have chromate in the presence of water. That's the equilibrium it sets up. So this is the Ka value that was given in the problem. 1.5 times 10 negative 6 is the acidity constant for this acid. It's given by these concentrations and there. If the hydrogen ion concentration then is going to be this, so I can just plug in the values. The HCrO4 minus concentration that we calculated was this minus whatever reacted. This is what we had. This is what reacted. And then multiplied by the 1.5 times 10 negative 6 divided by the 3 times 10 negative 7. So I can solve for that. So the hydrogen ion concentration that we would have that would give us enough hydrogen ion to keep the chromate concentration from reaching saturation would be this concentration. I can solve for the pH 2.46. So if I get this more acidic than 2.46, the precipitate won't happen. If I go above 2.46, it will precipitate. Okay, so I'm going to skip this because this is this, well, no, I'm not. I'm going to do a table with you. We're not going to do the actual calculation. So we'll do an ice table for this problem. Calculate the concentration of silver ion when 0.1 moles of silver nitrate is dissolved in 250 milliliters, 0.25 molar ammonia, and the formation constant is 1.7 times 10 to the plus 7. These form very highly, remember. All right, so the concentration of silver ion to start out with was that. Concentration of ammonia was that. And the concentration of the complex was 0. So if the complex was 0, the equilibrium is just right. So this will decrease by X. This will decrease by 2X because there's 2 ammonias. And this will increase by X. I can put these numbers together like this. And now set up the equilibrium constant expression. X divided by this is equal to my constant. If this turns out to be a cubic equation, you can solve it. I won't ever ask you to, but you can solve it, and you get X is essentially 0.04 molar. So the concentration of silver ion is 0.04, what we started out with, minus 0.0399 there. So its concentration is very small, 1.37 times 10 negative 7th molar. And that's what we sort of expected to happen. Solubility of barium iodide, this is a 4 ion. So let's calculate the KSP. This is your checkpoint problem. And again, work these out. Now be careful. This is going to be barium plus 3 and 3 iodide ions is what it's going to form. So remember, when you get ready to do that KSP, the KSP is going to be, the barium concentration would be S, the iodide concentration would be 3S, and it's cubed. So this is going to be 27S to the 4th power is the KSP. So I give you that much. Work on it on your own and then go to the discussion page. Okay, that completes our lecture for today. We covered a couple of important concepts: the common ion effect on a weak acid, weak base equilibrium, and the KSP. These are all of the subjects that's going to be present when we do our, these are all the things that will be present when we have our exam on Monday. So Friday's lecture will be mostly review, assuming you've had the chance to go back in and work through the checkpoints, work through the practice exam, and then when you come in on Monday, on Friday, be sure that you have your questions ready. There's 30 questions on the exam. There's no way that I can explain all of those in a reasonable hour lecture. So I would prefer to answer your questions first over lecture material, anything that we've covered for this unit. Ask those questions and we'll deal with that first. And then I'll ask you for questions on the practice exam. We'll work those out next. And if there is remaining time, I'll look at the questions we haven't looked at on the practice exam, and I will then go in and work those problems to help you understand them. So that's all we have to do for today, and I'll see you on Friday. Have a great afternoon and evening. Bye.